Okay, good morning, everybody. Or if you're joining us from elsewhere in the world, we probably should say good evening to you. Welcome to this very exciting webinar with award-winning bioanimator, Dr Maja Divjak. My name is Dr Claire Fideli. I'm the Research Communications Officer at the Peter MacCallum Cancer Centre, where we are lucky enough to have Maja as our resident biomedical animator. And for those of you who are joining us from elsewhere around the world, Peter Mac is the largest cancer-dedicated hospital and comprehensive cancer centre in Australia. So a little bit of background on Maja. She did her PhD analysing tumour necrosis factor in asthma, but she was keen to bring together her love of art and science in some shape or form and went on to study 3D animation at the Australian Film, Television and Radio School. Before joining Peter Mac, Maja honed her craft under a fellowship with world-renowned bioanimator Dr Drew Berry at the Walter and Eliza Hall Institute of Medical Research here in Melbourne. She's created animations and stills for Promega and was the resident science animator at the Gene Technology Access Centre. Maja is an award-winning bioanimator, and her most recent film entitled What Goes Wrong in Cancer has been awarded a number of awards, including a Platinum Remy at the World Fest Houston International Film Festival. It was a finalist at the Raw Science Film Festival. It was a winner of the Biocommunications Association Medical Education Award in the category of motion media, and it's an official selection at the Doctors Without Borders Film Festival, which I think you'll agree are very impressive awards for Maja. She'll present some of the elements of this incredible award-winning project in today's webinar, but I also encourage you to watch the film in its entirety, and I will provide the link in the chat function of this webinar to the YouTube video so you can watch it in its full. Before I do hand over to Maja, just a few housekeeping points. We will have time for questions and answers at the end. So please submit your questions via the Q&A function in Zoom at the bottom of your screens. And you can also upvote other people's questions if you wish. And this webinar is being recorded and will be made available to watch on demand later on Peter Mac's YouTube channel. So without further ado, I'll now hand over to Maja.
Okay. I'll just share my screen. How does that look, Claire?
It looks good if we just get it perfect.
Okay, great. Thank you, Claire, for that lovely introduction, and thank you also for inviting me to speak today. It is an honour and a privilege. And thank you everyone for joining us. Good morning to everyone in Australia, and good evening to those in Europe, the US and elsewhere. So today I'll be taking you on a journey into animation as a tool for visualising biology. So we're going to talk in depth about communicating science with biomedical animation. I'll just give you a brief overview of what we're going to cover in today's webinar. We'll take a look first at what biomedical animation actually is and why it's so important. I will then cover how I actually came to be an animator, which was something of a circuitous route. We will then take a look at the steps involved in a typical project and what actually happens creating a project from beginning to end. I'll discuss some of the artistic devices that I use to direct the viewer's attention and to facilitate understanding. We'll take a look at the software that I use and also the main tools within that software. And then we'll cover some of the challenges and joys of being a biomedical animator. So let's start by defining biomedical animation and what it actually is. It's a way of translating complex biology, often very complex, into a visual three-dimensional format that accelerates understanding, engages people with science, and most importantly for me, illustrates the breathtaking beauty of biology. So let's have a look at what it actually does. This first point is really important. It makes the unseen molecular and cellular world visible. The only way that you can actually view molecules at the moment, actually see them, is with an electron microscope. And since most people don't have access to even a basic light microscope, let alone an electron microscope, which is a very large, specialised piece of equipment that requires expert knowledge to use, biomedical animation is a way of making that world visible to everyone. And so you may ask, where do I actually obtain the data? What kind of data do I use when I'm creating my biomedical animations? And I mostly rely on data in a freely available public repository called the Protein Data Bank, which at last count contains about 164,000 protein structures, 47,000 of which are human sequences. And the data that I obtain from the Protein Data Bank is primarily obtained by X-ray crystallography. So I'll give you a little bit of a background of X-ray crystallography and what that is. So when you're actually creating proteins, so when you're expressing proteins and then you crystallize them, this is quite a technical, difficult process and is something akin to witchcraft. But if you were a protein crystal person and you like to grow proteins and crystallize them, you will do this first. And then if you want to find out what the protein actually looks like, you can take your beautiful protein crystal and you can take it to a place like the synchrotron at Monash University, and then you can bombard it with X-rays. And the way that those X-rays actually hit your protein crystal and then the trajectory that they take when they bounce off the protein crystal in XYZ space gives you a visual readout of what the protein actually looks like. And so those XYZ coordinates are deposited in the Protein Data Bank, and I'm able to access those data coordinates, bring them into my animation software, and that gives me a visual representation of the protein structure that I'm interested in working with. So that's how I actually obtain the data that I work with in my animations. So now that we've had a little foray into X-ray crystallography and protein crystals, let's get back to biomedical animation. What else does it do? It promotes understanding of new discoveries that might otherwise be really difficult to explain with text or even with simple 2D imagery. This one's quite interesting. It can actually offer insight to scientists. A lot of the scientists that I work with are not structural biologists. They tend to work in terms of quantities and qualities and how proteins interact. And so they're not used to thinking about what their proteins, their hero proteins actually look like. They think about them in more abstract terms and concepts. And so when they actually see their hero molecules in action, when I've animated them, they can often say, oh, I really never thought about the molecule looking like that or interacting that way or joining, with the domains that it actually interacts with. And so it can actually inspire ideas about the function of their favourite protein and its purpose as well. So it actually serves to inform scientists and their research as well. Biomedical animation it's a visual presentation of biology, but it's not only useful in an educative sense, it can also be a really beautiful work of art. And I get comments in that regard all the time. Oh, you make disease look so pretty, is a favourite comment of mine. And it can be the gift that keeps on giving. So the animation in itself is not always the final endpoint. You can take still images from your animation and you can print them out on beautiful materials like perspex and acrylic and foam core, and then you can exhibit them on wall space, which is what we've done at Peter Mac. And we've added an extra dimension to these still images using an app called Artivive. And you download this to your smartphone, you look at the image through the app, and the app then plays an underlying animation that's associated with that image. So the image looks like it comes to life as you're looking at it through your phone, which as you can imagine is quite an inspiring and engaging process that patients are really enjoying on level 7 in our atrium area. We've also gone off into really interesting territory, developing an interactive resource for KRAS mutant cancer patients. So this is a visual resource that will assist the clinicians in explaining this specific cancer biology to the patients, and also assist them in understanding how a newly developed drug can assist with their particular mutation. So this is in development at the moment, so it's a watch this space for this one, and I'll keep you all informed as this develops. So why is biomedical animation important? 60% of our brain is devoted to processing visual information or performing vision-related tasks. So we're visual creatures, and we have been since the days we scanned our environment in search of food. But these days, with the invention of the internet and the absolute rise and domination of social media, we're becoming ever more visually focused. So visual strategies are therefore the best approach for engaging audiences with science. It acts as a conduit from the lab to the public. It gives insight into research that's been conducted in the lab. So a lot of people out there that are non-scientists tend to think that scientists are very strange people who wear white lab coats and who do nefarious things behind closed doors with their tax dollar. So it's up to us. We really need to address this mistrust, and it is a mistrust in the public, by opening the lines of communication to better inform what it is that scientists are actually doing with their tax dollar. And biomedical animation does this. So through a process of education and understanding comes a process of inclusion. So biomedical animation serves to actually build a bridge between the secret world of the lab and the general public. It removes fear of science. So a lot of people are afraid of science. They find the language intimidating, they find the concepts intimidating, and it makes them retreat. And so biomedical animation actually makes science accessible through visual rather than abstract concepts. And another really important point for me is that it gives an appreciation of the beauty and the drama going on in your own body. And it facilitates a connection with your biology. You have a whole universe of cells inside your body and a whole universe of molecules inside those cells. And most of the time, everything just interacts and works and functions without you even having to think about it, except when things go wrong in situations like cancer. So it's really important that you appreciate that your body is an incredibly beautiful machine and that you really should respect it and look after it. So let's take a look at why it's really important. You could say this: DNA damage consists of single strand breaks, which are discontinuities in one strand of the DNA helix, double strand breaks, where both strands of the DNA duplex are severed, DNA kinks, which occur when stacked base pairs become unstacked, causing DNA to make a sharp turn, and pyrimidine dimers, which cause two separate DNA helices to stick together. And this is the likely response you'll get. Huh? Or you could show someone this. Just a quick point, while I'm showing you animations, I won't speak over the top of them because we found that that really affects the quality and causes stuttering and jittering. So when I come to a video, I will explain it first and then I'll show it to you, and I won't speak over the top. So I'll just show this to you now.
DNA encodes the information needed to make proteins, which are the building blocks of our body. To keep 2 meters of DNA organized within the nucleus, it is wound around special structures called histones, much like thread on a spool. Damage to DNA can include single-strand breaks, double-strand breaks, changes to the DNA code, DNA kinks, and DNA sticking together. It has been estimated that an individual cell can suffer up to 1 million DNA changes per day.
And you can just see how that makes so much more sense than that previous piece of text, and how someone would understand that so much more readily. So I'm going to go into a bit about me now and how I came to be a biomedical animator. So, as you've probably guessed, I work at the interface between art and science, and I use animation for the purposes of scientific education and illustration of biological processes. So I love inhabiting that nexus between art and science. So how did I become a biomedical animator? I went right through the academic system to postdoctoral level before I realised that maybe a world in research wasn't really for me. And then I went into scientific sales for a really long time, for about 10 years. And it was during that time that I became increasingly aware that my artistic side needed a much more creative outlet. In high school, I was involved in a lot of creative subjects. So I studied French and art, and those more sort of lyrical pursuits took a back seat when I went on to study science in a really intense kind of way. So that kind of side of me really took a back seat for quite a long time. So I was really struggling with how to bring art and science together, which is what I really wanted to do. So I wanted to marry those two sides of my nature, and I couldn't imagine how that would happen. So I was asking the question, where is the art? How can I find the art in my life again and bring it back into my life? And as luck would have it, I met a lovely person called Dr. Drew Berry, who is considered probably the world's leading component of the art of scientific animation or biomedical animation. And it was just one of those really chance, serendipitous things. The Walter and Eliza Hall Institute was part of my sales patch at the time. And yeah, I just happened to mention to one of the receptionists that I was really bored and that I was trying to think of a way of bringing art and science together. Just excuse me for a moment, would you please? My biology is failing me. Yes, I just happened to mention to one of the receptionists that I was really bored and I was really struggling with a way of thinking about art and science and trying to make them mesh. And so she just dragged poor Drew out of his office and yeah, he was really obliging and showed me his work. And it was one of those aha moments for me. I looked at it and thought, well, this is just the perfect synergy of scientific rigour and visual representation. It was beautiful and it was scientifically accurate. So I thought, yes, this is what I want to do. So I set about retraining to become an animator. I went off to Swinburne and I studied multimedia for about a year, doing web design, 2D and 3D animation, life drawing, sound design, and so on. And then I went to the Australian Film, Television and Radio School and studied 3D animation in a really intense way there. And then I just set about working on my own projects, animating my PhD, which is a really great piece of advice from Drew because you know it so intimately. And yeah, working on a few freelance projects here and there. And that was enough to get together a decent show reel. And as luck would have it, I was offered an 18-month fellowship with Drew at WeHi, where I learnt most of what I now know. So that's where I found the art. And yes, I'm currently a biomedical animator at the Peter MacCallum Cancer Centre, as Claire mentioned. And after completing the fellowship with Drew, I was science animator at the Gene Technology Access Centre. So there's me in a nutshell. So let's take a look now at creating a biomedical animation and what is actually involved in creating one from A to Z. So you need to begin by defining your animation project and what it's going to be. So at Peter Mac, we're really lucky because we're not only a world-leading specialist cancer hospital, we also have an integrated world-leading cancer research program. So we're able to select from the most interesting and cutting-edge projects, and we can animate them and then bring them to the world. And so that's how we determine the project that we're going to work on. You then need to talk to the associated scientists if they're available. And of course, at Peter Mac, I'm really lucky in that I'm able to speak to those scientists. They're right there. They're often really happy to talk to you about their work because they love it and they want to share it with the world. And so it's such a fantastic resource to be able to speak to the actual scientist who's working on that subject about their work, get the facts straight, make sure the story flows in the correct way, you know, talk about the molecules and whether they're correct and so on. So yes, talk to the scientists if you can, because that's a really important resource. You then need to read a lot. So I spend a lot of time reading the scientific literature so that I can get a handle on the subject. You have to understand it in order to be able to animate it. And I find that consolidating that understanding really helps if you write a literature review. And I often then use the literature review and I distill that into a visual form when I create the storyboard. And as you can see, this storyboard in the bottom right corner there, this looks like a comic strip that outlines the shots in sequential order, what's going to happen in them and how they're going to look. Then I will typically write a script, and I like to do that at this point because it really helps you time the length of the shots according to what needs to be said to explain the shot. So it helps the animation to flow really well. Some people can do this really intuitively. Drew never does the script at this point. He always writes his script last, but he seems to have an innate understanding of how long to make the shots in order for the flow of the animation to work nicely. But I like to write my script there. You then need to assemble your models from the protein data bank, which we discussed previously. And up until recently, I used software called Chimera, and you can see an example of that here in the left, over on the left here. I've got an EGF receptor with SHIC1, GRAB2 and SOS1 here. So yeah, you need to assemble your protein structures so you can build a molecular assembly. And often you will find that there are only portions of the whole molecular assembly available in the protein data bank. And there are often lots of intervening sequences that are simply unavailable in the data bank, often because they're very fluid and floppy and they don't tend to crystallize all that well, like these squiggly sequences that you might be able to see in here. So yes, you assemble your models from the protein data bank. You can do that using Chimera, or you can do it in the Maya software itself, which I will discuss a little bit later on. You then need to rig and animate them in Maya. And this is an example of the Maya interface over on the top right corner here. So what you can see on the left in Chimera has been transferred into Maya, and we're looking up at it from below. So you can't see the EGF receptor at the top because that portion of the molecule is extracellular. We're looking at the intracellular portion here. So yes, you need to rig and animate your molecules. So rigging often involves controlling the molecular assembly with a skeleton of joints and bones so that you can actually move and rotate and articulate the domains of the molecular assembly in much the same way as our joints and bones allow us to move and rotate our limbs. So you've got a rig that can control your assembly, and then you need to animate that rig, and you do that in Maya as well. And there are various ways of doing that. I will discuss some of those in a short while. So once you've got your molecules rigged and then you've animated them, you can actually test them out and see what they look like using this process called a play blast in the bottom right corner here. So I perform a lot of these throughout the animation process just to ensure that things are interacting in the correct way, that the timing is right, that the animation looks correct, and that you're happy with it. So I'll just show you an example of that. This is really rough and ready because it's just taken from the actual Maya working area, the interface. So I'll create a lot of those as I'm going along animating, just to make sure that everything is turning out the way that I want it to and that it looks good and that I'm happy with it. So you then are able to texture your molecules, add pretty colours, light the scene so that it looks beautiful and radiant. You add cameras and camera moves. So it's a lot like being a digital director in a lot of ways. You then need to render your scene. And so rendering, I'll just explain that a bit. Every second of animation consists of 25 frames, and every frame in my situation consists of 1980 by 1020 pixels. And the process known as rendering is where the computer actually has to build each frame pixel by pixel. And this can be a really time-consuming, labour-intensive part of the animation pipeline, depending on the complexity of your scene. Yeah, so that's the process of rendering. You have to actually build each frame pixel by pixel. So then you have to put together all those frames into a coherent whole. And this process is called compositing. And I do that in my software of choice, which is After Effects. You may be quite familiar with software like Premiere or Final Cut Pro. They are rather similar. Yeah, so it's at this point that I composite, put all those frames together, that I edit the shots, get the timing right, add special effects, add labels and captions. And this is where everything really starts to look more like the final result. And it's quite an exciting phase of the process, and I quite enjoy it. Once you've completed your compositing, you then are coming to the final stages of the animation. I always add sound effects to the animation, and I have worked with a lovely fellow called Adam Hunt for about the last 7 years, and he adds all the pops and whirs and all those kind of strange buzzing sounds that actually really direct the viewer's attention and really bring the whole animation to life. And then finally, of course, we add narration, and I'd really love to thank Dr Claire Fideli for her beautiful narration that she created for our latest animation, What Goes Wrong in Cancer. So let's take a bit of a look now at my artistic approach to biomedical animation. The story dictates the design of your shots. So what you're trying to say needs to inform the look and the feel of each shot and not the reverse. So the way the shot looks shouldn't be directing the story. The story is always king, as the folk at Pixar are really fond of saying. You can use camera movement and lighting to great effect. You can use it to really direct the viewer's attention, and you can use camera moves to take the viewer on a journey from point A to point B. Choice of colours. This is an interesting one. It's contentious. Most molecules don't actually possess colour. The exception to this, of course, is our classic favourite green fluorescent protein. There's indigo, ferrocene, perylene, and myriad others that are coloured. But on the whole, most molecules aren't actually coloured. So there are some purists out there who say that you should actually create animations in grayscale because it isn't realistic to colour molecules. There is a woman known as Monica Zoppa who does this. She creates her animations entirely in grayscale, which is quite a feat in my opinion, considering that you really don't have the colour aspect to drive the viewer's attention. So it's quite a feat, and you should take a look at her work. It really is rather beautiful. You can actually use colour to great effect though. You can use it to invoke a disease state. So you can give ideas, or you can indicate inflammation using warm, rosy, hot, red, orange kinds of colours. And you can use really murky colours like, dull, muddy yellows and browns to indicate cell death by apoptosis, for example. And this tends to register subconsciously with the viewer. They are inherently aware that this is what you're trying to say. You can see the image over in the top right there. This is an image of the KRAS mutant protein, and I've coloured those in red there to indicate that this is a situation that's dangerous because this mutant protein leads to out of control cell division and possible tumour formation. So I've used the red to indicate that this is not a happy situation. You can use colour really well to delineate the different functional parts of molecules, and this can be completely arbitrary. So, for example, in this lower image here, I've illustrated BRCA1 in sea greens, and this doesn't really give any indication about whether this molecule is good or bad, although I've lost my cursor. Where are you? Here we are. If you look at this sort of paler green area here, if you have inherited mutations in this area, this can lead to a particularly insidious form of breast and ovarian cancer. But I haven't made any assumptions about whether this molecule is good or bad using that green colour palette. So often I choose colours simply because I find them beautiful, but in the case of animating cancer biology, that has presented a bit of a conflict for me, because is it appropriate to make something that people find uniquely terrifying look beautiful? I'm actually hoping that the colour, although it is beautiful in itself, actually makes no comment on the relationship of cancer to human beings, and that it instead actually highlights the complexities and patterns of the biological molecules themselves. I use glows quite a lot. These are really fantastic for highlighting cellular or molecular interactions. For example, insulin binding into the receptor pocket. You can highlight that with a glow, and so a person will be immediately attracted to that action and will understand that some kind of molecular handshake has taken place. Sound effects. As I mentioned previously, they're really amazing for directing the viewer's attention and facilitating understanding. And they are not a secondary consideration at all. The sound effects really bring the whole animation to life, and they're actually integral to the whole. So let's go into some technical aspects. we'll take a look at some of the software that I use when I'm creating my biomedical animations. I use, or I have used very extensively in the past, Chimera and Chimera X for assembly of protein fragments from the protein databank into complete structures. Although more recently I've started relying more on a plugin called Molecular Maya, and so you can actually do this directly in the animation interface. So I'm not using that as much anymore, but I still rely on it quite heavily. The animation software that I use is called Autodesk Maya, strangely enough. And this is industry standard animation software that's typically used throughout Hollywood. And it's fully customizable with scripting from the command line if you wish to work that way. As mentioned, I work really intensely with a plugin that you're able to insert directly into the Maya interface called Molecular Maya, and that is by a lovely collective called Clarify, and you can see the contact information there if you're interested in it. So it's a plugin that allows you to import PDB files, so those XYZ coordinates that I spoke of earlier, into Maya in atomic, surface or ribbon formats. And this is fantastic because you used to have to do it from the command line, and that took hours. However, it's also been developed a lot further lately, and it offers options to actually build your molecular assemblies, which I've been doing a lot lately and have found it to be really useful and saves a lot of time. And you can also create semi-automated rigs for your assemblies as well. You can build cytoskeletal elements such as actin, and there's also the option for animated double-stranded DNA, which I have used extensively as well. And as mentioned, Adobe After Effects is the software of choice for compositing, editing, special effects such as zooms, vignettes, and film looks, glows, labels, animated arrows and pointers, and captions for the hearing impaired. So let's dive into Maya a bit further, and we'll take a look at the dynamics set of tools, and these are the main tools that I use within Maya. So it's a set of tools that uses rules of physics to simulate natural forces, and so it allows you to create realistic motion without traditional keyframing. So you specify the actions that you want your object to take, and then the software figures out how to animate that object for you. So in the What Goes Wrong in Cancer animation, I used particle systems, and I used these to animate lipids in the cell membrane. And I've used these really extensively in the past to illustrate release of chemical mediators. So particles can be emitted anywhere you like. They even can be emitted from actual objects themselves. And you can animate them using force fields such as turbulence, gravity, vortices, and so on. I also use cloth systems, which, as the name suggests, allows you to animate clothing on characters. But I find for biomedical animation, it gives molecules a lovely organic fluid motion and makes them soft and deformable. A lot of people have this idea that molecules are like concrete and that they kind of smash together, which couldn't be further from the truth. They do actually interact and bounce and kind of mold around each other in that fluid sort of way. I also use hair systems, again, which, as the name suggests, is for animating hair on the heads of characters. But in my situation, it's great for giving long rope-like structures whipping motion. So you can see that there are systems that are typically used in Hollywood to animate characters that can be used to great effect in biomedical animation. So I will show you some of those effects now. as explained, I will cover what's actually going to happen in each shot first, and then I'll play the shot and I won't speak over the top of it because that really affects the quality. So creating the lipid bilayer here, so the cell membrane, what I've done is I've created two planes that represent each side of the bilayer, and then I've animated the planes with a particle system, which is driven by turbulence to give jittery undulating motion to the planes. So they wave like that and they also vibrate like that. I've then applied some animated lipid molecules to those animated planes. And so they have their own individual inherent animation. And so that gives a really dynamic membrane effect. So you've got the individual lipid animation and then the overall undulating and jittery animation. And the molecules that you can see here lying underneath the membrane, so in pink, blue and lavender, they've been converted to cloth, which gives that lovely organic motion that I've described. And they also collide with each other and they're held in place with constraints. So as the cloth, one really important point to bear in mind is that as the cloth and the particle systems are part of the overall dynamics menu, they can actually interact and collide with each other, which is very desirable. So let's play this and you can see all of that in action. Ooh, that wasn't supposed to happen. So let's take a look now at some hair animation, some hair system animation. So here I animated the long snake-like structures of the mRN machine, which you can see over in this bottom right-hand corner in blue and lavender. So these long snaky structures here of the NBS and the RAD50 components have been animated using hair systems. So first I built a skeleton of joints and bones to control the machine overall. And then I animated that skeleton using hair systems, which were driven by turbulence fields. So it gives that appropriate wavy whip-like motion. So I'll just play that now. I'm getting a lot of stuttering, so I hope that the quality is not as bad as it appears on my machine. This is one of the vagaries of Zoom, I guess. Okay, so let's move on to a system known as MASH. And this is a relatively new addition to the animation arsenal in Maya. It's been around for about the last 4 years, I think. And it's Maya's motion graphics toolkit. And what it does is it allows animation of multiple objects using procedures, that is mathematical equations, rather than manual keyframing. So it's great for creating really large cityscapes, forests, gardens, and in my case, animating really large numbers of molecules. So it offers a lot of control and flexibility and is also great at saving time. And I used this as a new method of animating the lipid bilayer in cell membranes. So this is quite a rough and ready test, but it'll give you a good idea of the process and how it looks when you're actually testing things out. So I'll explain how I did this. So what I did was I created 3 small clumps of upper and lower lipids, and I animated them with MASH dynamics, excuse me, to give overall jittery movement. So movement in X, Y, and Z, and that also sort of jittering, vibrating movement as well. I then made the same 3 clumps animated with cloth, so to give actual individual motion to each lipid, like that. And then what I did was I constrained the cloth animation to the MASH animation. So now you have sets of lipids with internal individual animation and then that overall jittery XYZ movement. And then you can use these 3 groups to create instances in a really large dynamic MASH network. So you can create a 1700 lipid bilayer, as I have done here. So let's take a look at that. And I've lost my cursor again. Come back. Oh dear. There we are. So in retrospect, I would like to make the variation, increase the variation a bit. There's a little bit of a uniformity to the movement of the lipids there. So I would actually go back and add some further variation to that to make it look a lot more random. So let's cover some of the challenges and joys of being a biomedical animator. Unfortunately, there are no specific courses or career path in Australia. So you have to make do with entertainment industry offerings, and you have to know how to actually apply those to a biomedical or scientific animation situation. There are some really specialised courses in the US and in Canada, particularly in Toronto. So if you wanted to actually study biomedical animation specifically, you could go there and do that. And there is quite a defined career path for a biomedical animator in Europe and the US and Canada. And there are lots of scientific design houses over there that you could join if you so wished. But at the moment, there's really nothing formal or established in Australia. So as you could imagine, there are few job opportunities in Australia in this regard as well. There's myself at Peter Mac, there's Drew and his team at WeHi, there's Kate Patterson at the Garvin in Sydney, and John McGee's group at UNSW, and there's a woman at QIMR. And there's a smattering of freelancers. So there are very few of us in Australia, and you really have to make your own job opportunities or freelance. But as mentioned, if you went overseas, there is a lot more out there available to you. Creating an animation, as you can imagine, as I've explained the process, can be a really painstakingly slow and frustrating experience. And you have to have the headspace to be able to cope with that, because progress can be really, really slow. This can be both a challenge and a joy, working alone. Working alone can be great in that you have complete autonomy and artistic control over the project from beginning to end. But you don't have someone to bounce ideas off. You can't turn to the person next to you and say, what do you think of this? Do you understand what's going on? Do you like this colour scheme? How would you approach this particular animation problem? So it's a double-edged sword. It is great in some ways and not so great in others. Again, a challenge and a joy. Constant problem solving. as you've probably worked out, you need to bend the computer to your will. So you are presented with animation problems that need to be solved. You need to make the computer do what you want in order to solve an animation problem. And this again can be really time consuming. You can go down many different paths and end up at dead ends before you actually solve the problem. So yes, it can be really frustrating and time consuming, but so rewarding when you come up with the answer and something works beautifully and you solve that problem, and it can be great. Again, double-edged sword. I love this. I love combining my skills as an artist with my skills as a scientist. So being an animator ticks all the boxes for me. So it satisfies the lyrical, creative side of my brain, as well as that really didactic, analytical side of my brain. So very satisfying for me from those 2 points of view. It's really creatively rewarding because in the end, you actually have a tangible result. You have this beautiful thing that you can send out into the world for other people to enjoy, or not, as the case may be. So to summarise, biomedical animation is a really powerful tool that makes the unseen cellular and molecular world visible. It enables the viewer to understand scientific concepts that might otherwise be really difficult to explain with text or with 2D imagery. Visual technologies such as biomedical animation are the best way to engage people with biology, given how visually focused we are becoming. A whole project, as you've seen, follows a particular process from start to finish, but there's a lot of to and fro between the various phases and steps. And you can use a number of different artistic strategies to direct the viewer's attention and to facilitate understanding, like lighting, camera moves, glows, colour, of course. I tend to use lots of dynamic simulations, such as particles, hair, and end cloth in creating my animations. And recently I started using MASH, which is a new tool for controlling animation with procedures rather than keyframes. So with that, I would like to acknowledge a few people. In particular, I would like to acknowledge Professor Ricky Johnston, Dr Carol Gins, and Professor Rick Pearson for believing that biomedical animation is a worthy enterprise at Peter Mac. I'd really like to thank Dr Claire Fideli for her beautiful narration skills and her wonderful script editing skills. My scientific advisors at Peter Mac include Ricky, Rick, Claire, Dr Elaine Sanich and Professor Igal Haupt. Also, big thank you to Professor Mark Glover at the University of Alberta, Professor Kumkum Khanna at QIMR, the communications team, the Cluster 9 Research Labs, and finally, thank you to the Peter Mac Cancer Foundation for support of this initiative. So thank you everyone for joining us. I hope that you enjoyed this and got something out of it. Happy to take questions now, but if you wish, you can contact me on Twitter or via email. Thank you very much. Over to you, Claire.
Okay, thanks, Maya. And can everybody please give Maya a wonderful virtual round of applause for a fantastic webinar. Very, very interesting and fascinating to see how you have taken your scientific background into the world of bioanimation. I've lost my cursor as well, so a lot of technical fun happening on Zoom today. Here we go. Okay, so I'd like to ask if we've got any questions for Maya, submit them via the Q&A button at the bottom. We do have some questions already submitted, so we might get started. The first is, hi Maya, did you have any background in computers or technology before you started doing bioanimation, and how long did it take you to learn?
No. I was one of those people who, I was 21 when I first touched a computer, because personal computers as an entity actually didn't exist when I was growing up. So the first time I laid hands on a computer, I was 21 and I used it to write my honours thesis. And it was one of those Mac SEs that had a screen that was literally this big. It actually made life harder than if I'd written it by hand, I think. So no, I actually didn't have any computer science background at all. I didn't grow up comfortable around computers particularly. For me, I felt like I needed to go and do some courses to actually gain the skills needed to become an animator, which is why I went to Swinburne and then went to the Australian Film, Television and Radio School. Drew always gives the magic number of about 5 years before you can really be creating animations of a high calibre and of a standard where somebody would actually want to employ you in a full-time capacity. Maya is a fairly difficult program to learn. It's hugely complex and has so much power and flexibility. It took me a good 6 months to get comfortable with it. But once you do, you kind of fall in love with it. So yes, no, I didn't have much computer experience before I went into this world at all. And it takes a bit of time to get comfortable with it, but once you do, it's great. It's really rewarding and satisfying. I hope that answers your question.
Hi Maya, as someone who's coming to the end of their PhD and wanting to cross over into the animation field professionally, what would be some good next steps? Do you have any recommendations for societies or events to attend or people to meet?
Yes. First port of call would be the Clarify website. So www.clarify, which is spelled CLARAFI.com. Hop on there and have a bit of a read. They have a lot of information about software, techniques. There's a careers page where you can meet people and learn about their career paths and trajectories. That's a really good port of call. You can come and talk to me, of course. I'm happy to advise you as well. It depends on how comfortable you are with software at the moment and whether you're actually already creating things. One really great piece of advice I got was to animate my PhD by Drew. So because you know it so intimately, you know the story, and it's a really good place to start if you want to get into animation. I actually have a list of links that you can visit that will kind of get you started in that area. So drop me a line and I'll forward those to you, and that will kind of get you reading and get you learning a little bit about the world of biomedical animation and where you could take it. But definitely look at Clarify. That's a great place to start off. Yeah.
Hi Maya, thanks a lot for sharing part of your animated world. What would be your advice for a PhD student like me or someone else who don't have a lot of knowledge about bioanimation, but who would like to incorporate bioanimation into scientific life and projects? Thanks a lot for all of this beautiful work and congratulations.
Thank you. So again, I'm not sure whether you're asking like how to kind of include bioanimation in your kind of own sort of research world, or whether you kind of want to go off into that world. Yes, as I said, if you want to kind of make a a detour into the world of bioanimating, if you're thinking of becoming one, again, drop me a line and I can send you some information about sort of taking your first steps in that area. Otherwise, if you actually want to kind of include bioanimation to tell your research story, there are animators out there who freelance and would be freely available to help you do that. Again, I can point you in the right direction if you're looking for someone to help you in that regard. So I hope I've answered what you were asking there. I'm not quite sure I have, but anyway, send me an email and we'll take it from there.
Thanks a lot, Maya and Claire. How long did it take you to finish the cancer animation project from start to finish?
Wow. It took about 1.5 years. I had a few glitches along the way. The Kirsten Rass, the K-Rass animation in the latter half of the piece, I'd actually modelled the K-Rass structure incorrectly, and I didn't have it interacting below the cell membrane as I showed it to you today. So I actually had to redo that portion of the animation, which sort of added another 3 months to things. But, you know, these kind of things can happen, these kind of setbacks. But I'm so glad that I did actually revisit that part of the animation and redo it, because it would have been a nightmare if I'd sent it out into the world and not had the structures and the interactions correct. So yeah, it took about 1.5 years from beginning to end. So that's, you know, that's all the reading, that's the talking to everyone, that's the building, the animating, you know, the lighting, the rendering, the compositing, the sound effects, Claire. Yeah, so you can see that it's, you know, much like a research project. It takes a long time and there's a lot involved. So yes, about 1.5 years.
Hi, Maya, great presentation. Do you ever get a scientist criticise or disagree with your take on what is happening in a particular scenario, and how do you handle these questions?
I haven't really so far. That could have happened with the Kirsten Rass, so I'm really glad that I didn't actually experience that. It tends to be minor things like, oh, I wouldn't have used that colour, or maybe I would have moved this a little bit over here. I've never had a direct criticism about structures or the interactions and how they've unfolded. But yeah, I think I think if that did happen, then, you know, you'd have to be ready to defend yourself and be able to show them the papers that you got your data from, your information from. So yeah, you definitely can't go around making this stuff up. You have to read it. Yeah.
Thanks,
Good
Maya.
question.
Great presentation. You're the first postdoc I've met virtually to cross over to animation. Would any specific discipline in science, example chemistry or biology or biophysics or bioengineering, be helpful to grasp the scientific aspect?
All of those things, definitely, all of those things. Yeah, so if you have a scientific background, then you have the tools necessary to make the jump. And yeah, it's really important. If you're going to become a scientific animator, you have to have scientific experience and scientific knowledge. It would be really difficult to read a Nature paper, for example, Paul Beavis's paper that was released recently, and actually understand it and make sense of it and distill it into a visual format if you didn't have that scientific background. So yeah, if you've got it, you can make the move.
Hi, Maya. Thank you for the wonderful presentation. Do you see yourself expanding your animation team at Peter Mac in the future?
Lovely question. I would love to do that. I would love to do that. Yes, yes. Yes, the plan is that I would definitely like to do that and take on some other team members. And I think that it would be great to grow the animation world at Peter Mac. I've only been around for a couple of years so far, so slowly. But yes, definitely plans to do that. It would be good.
Thanks a lot for the wonderful seminar. I'm an ex-researcher trying to get into the field. I love it, but struggle a bit to find the way. Any practical tips? I just heard about 5 years, but apart from that, again, thanks. People can dabble.
Wow. Again, clarify. This is a really great port of call because it is specifically for biomedical animation. And so it has all the tools that you need. It discusses software, and there's a really useful page where people talk about their careers. I'm on there, and there are a whole lot of other interesting people that are on there as well, including, you know, medical illustrators, bioinformaticians, and people like that. So that would be the first place I would go and look. If you want information about software and learning software and so on, please drop me an email and I will send you some information about that. But yes, look at Clarify. That's a really good place to start.
And just the last question, have you ever made any other types of animation?
No, not well. When I was at Swinburne, yes, I did 2D animation. And so, yeah, that was not scientific at all. It was, I did an animation about a geisha, which was fun. But not since then, no, I I find the world of molecules takes all my time these days. So no, I don't do any non-scientific animation at the moment, but I have in the past when I was actually studying. So yeah.
Wonderful. And there's one last comment in the Q&A, and I think it's a fantastic way to sum up or to end the session. And it says, "Thank you, Dr. Maja Divjak. I thoroughly enjoyed your presentation and your animations are beautiful." And I think that we can all agree that that is absolutely true. And I'd just like to once again thank you, Maja, for this fantastic webinar and also your wonderful films, which are just bringing science to life and are a joy to watch. We can all once again give a big round of applause to Maja. Thank you, everybody who's logged in and joined us today for the webinar. As I said, it will be made available later on the Peter Mac YouTube channel to watch back, and feel free to share that with your friends and colleagues. Anyone who else you think might be interested.
Thank you, Claire, and thank you everyone for joining us today. It was lovely to speak to you.